All right, so today we're going to do a little more integration by parts. My guess is that I'm going to finish up by 2, maybe 2:15. So we might cut out a little early today. Just remind me because I might just get going and lose track of time. So I've
office hours I'm going to go back to normal until after
till next Tuesday. Tuesday, yeah.
this coming Tuesday or Tuesday?
Well, this upcoming Tuesday, yeah. Yeah, it's just tomorrow and Monday I'm not going to be here.
What time do you normally get?
Usually I'm in there by around 9, usually around 8:30, but I'll say 9. Yeah, and then all the way till 1. Okay, so I have done the videos for the homework problems 1 through 25 are on the web. I just finished doing 26, 27, 28, 29, and 30. I haven't posted them to the web yet. So hopefully by the end of the day, all the problems for the homework for integration by parts will be posted. So because of that, I don't plan on entertaining any questions over the homework problems because there are videos for each one, right? So we did not finish the notes from last time, did we? We did not. So I would like to finish those. And we were working on problem F. I was going to do a quiz today, and this was going to be the quiz. Take out your integration by parts homework, and I'm going to come around and take a look at it. I wanted to see where you were, like how far you had gone. So if you wouldn't have had any homework, you would have had a 0. If you would have had some of it, then I would have scaled it up. If you would have had most of it, then 100. So just be prepared for that, because I plan on doing that probably on Tuesday. I need to make sure you're keeping up with your homework. I figured I'd give you the weekend, you know, and that way you can watch football and do calculus. Okay. All right, so here we go. Integral sine to the n of x dx. So n here is an integer, all right? See, we don't know what the power on the sine function is. So look at the instructions here, if you have your notes. It says, creating a reduction formula using integration by parts. So what I'd like to do is refer to you, get your formula sheets out. Where's my formula sheet? There it is. I'd like for you to look on your formula sheets. Do I need to have a quiz on whether or not you brought your formula sheet? Should I have a quiz on that too? All right, so let's say on Tuesday I'll check your homework and your formula sheets. And that'll be your one time. If you miss it, Tuesday, if you don't have it, you get a 0 on the quiz. If I check it again and you don't have it, you don't get to use it on the test. All right? So have it. Okay, so on this formula sheet, what is that? Extra homework? Okay, on this formula sheet, notice that they stop at 29, right? What do you look for? Go ahead. All these formulas stop at 29. I mean, all the formulas we stop at 29. I said in the book there's more, right? So on the formula sheets, do you see anything that has sine to the n power? There's really only, just number 6 has sine and that's it, right? We all know the antiderivative of sine. But there's nothing that says sine to the n power. But if you were to continue to look in the other formulas that you don't have, that you're not allowed to use on the test, there is formula 73 in the book. And let me write it down here for you. All right? It is sine to the n of x dx equals, all right, negative 1 over n sine to the n minus 1 of x cosine x plus n minus 1 over n integral sine to the n minus 2 x dx. Let me just double check that I had that right. Negative 1 over n, sine to the n minus, that's n minus 1 power right here. Cosine x, n minus 1 over n, sine, okay, that's it. Right, this is what we call a reduction formula. So let's try and understand how a reduction formula works. This says that if you want to integrate sine to a power, n, that you can turn it into this, and notice that this is just sine and cosine in here. This is a new integral, right? This new integral is different from the original integral in the sense that the power on it has what? Come down by 2. And so what you've done is you've taken sine to maybe like the 4th power, and now you've turned it into sine to the 2nd power. Understand? This formula allows you to take high powers of sine and break them down to a new integral. Does that kind of make sense? So let's just set up a problem, and then we're actually going to prove the formula. We're actually going to come up with the formula ourselves. All right? But for now, let's see how the formula works. So let me just change this problem right here. Sine, how bad do I want to go? Let's go sine to the 5th. Sine to the 5th power. According to this formula, this is equal to what? Negative 1 over 5 sine to the 4th x cosine x plus 4/5 integral sine to the 3rd x dx. Right? So we've taken a problem that was originally sine to the 5th power, and according to this formula, it's now, we just have to be able to figure out what sine to the 3rd power is. So what should we do? Do the formula again, right? How about the formula just on this piece? So I say this is equal to negative 1/5 sine to the 4th x cosine x plus 4/5 times, now big bracket here. This is where I'm saying I have my bracket. This right here is this formula again. This time n is being 3. Understand? So it would become what? Negative 1/3 sine what? Squared, sine squared x cosine x plus, remember n is 3, right? So 2/3 integral just sine. Ah. Will I need to apply the formula again? No, because I know what the antiderivative of sine is. You see that? So this reduction formula allows you to take high powers and break it down, break it down, break it down, break it down until you get to something you can handle.
I
Yes?
just want to make sure that until you get rid of the last integral, you don't have to put it plus c. Right?
That's right. Until you actually do the integration is when you could throw the plus c on there.
Because right now all we're doing is reducing.
Yep. So the answer here, I would just replace this with what? Negative cosine x, right? And then I would say plus c, right? And this would be your answer. You would have to distribute the 4/5 through, and that 2/3 would be in front of the cosine. So I'm not going to go any further, but you see how convenient and useful that is? You see that? Now, let's come up with a formula. This is going to be the hard part. Most of the time, reduction formulas, which is what I'm about to do, any time that I've ever asked a question on a test about a reduction formula, it's normally appeared in the form of a bonus question, because these are not very simple. They take some time. All right, let's go back to this. Okay, here we go. How do we come up with that formula? So this is not a very natural thing that I'm about to do, all right? But just tell me if you agree with this. First, I'm only going to be looking if n is greater than or equal to 2. Because if n is 1, do we even need a formula? No. And we're going to find out later today, if I have time, that if n is 2, we actually don't need a formula either. But n3 and higher, usually you want to try and have a reduction formula. So let's assume first n is an integer that's bigger than or equal to negative 2. All right, so do you agree that I could do this? I don't know what I'm doing there. I'm going to set up integration by parts table. Let me set up my table. I'm going to choose a u and a dv. But right now, I only really have one choice of u, right, Luke? What's my only choice of u right now? Sine to the n of x, right? That's really my only choice, and that forces me dv to be dx. If you do that, you're going to go nowhere. All right, it's not going to happen for you. So I'm going to do something tricky. I'm going to rewrite the integral. I'll put n is greater than or equal to 2 up here. I'm going to rewrite this integral like this. Do we agree that that's the same thing? I don't like the way I'm putting these powers in here, n minus 1. Is that the same thing? What's the power on this sign? 1. And the power on this sign? N minus 1. What happens if you have the same base and you multiply together? What do you do to the exponents? You add them. N minus 1 plus 1 is n. So that's the same expression, right? Now, why would you ever do that? Okay, that's what makes these hard, right? Is why would you ever do that? So if I do this, okay, if I do, let's see what happens if I let this be my u and this be my dv. So let's let this be sine n minus 1 of x is my u, and then dv is sine x dx. It's not obvious right now that this is going to get us anywhere, but let's see. So let's see. Is it too much to call on someone for this? Who wants to be called on? Someone hasn't been called on. All right, go ahead, Luke. Give me the derivative of this.
It would be sine n minus 2
Okay.
x.
All right. Sine n minus 2 of x dx. Right? So what, you just reduce the power? There's still more here, though. Remember, the power has to come out, right, when you're taking a derivative. N minus 1 out front, there's still something missing. Chain rule. Right? So n minus 1 is like a power. Look, sine of x to the n minus 1 is what we have, right? That's what that really means. When we take the derivative, the n minus 1 comes out. Then you subtract 1 from that. And minus 1 is minus 2. Then the derivative of what's inside, which would be?
It should be cosine, not sine.
What's that?
It should be
Well, no, because I still need to take the, that's not correct. But that's why I'm going through it. N minus 1 comes out, right? So the derivative of this is n minus 1 comes out. Now it's sine, take the power down by 1, n minus 2 of x. Now the derivative of what's inside, cosine x dx. That's du. Got it? So let me come back over here. Du equals, I don't have enough room here, so I'm going to go du equals, then n minus 1 sine to the n minus 2x cosine x dx. Y'all with me? Yes? Okay. The next thing is to integrate up the other side. So v is what? Negative cosine x. Yes? All right. So this integral is now, we are going to use that acronym. Justin, what's that acronym? It's not really an acronym, but what's that little thing that I've been using? UV minus voodoo, right? Ultraviolet minus voodoo. Okay, so ultraviolet, these two multiplied, right? Yes? Those two multiplied is negative sine to the n minus 1 of x cosine x minus the integral of voodoo. And voodoo is this, right? Voodoo is this. So what would we get here? Do we have any constants we can pull out? n minus 1 and a negative, right? So negative and an n minus 1. So why don't I pull that out? I'm actually going to write it like this. I need a little more space. It's going to be plus n minus 1 integral. Now what's still in there? Cosine squared and sine to the n minus 1. So I'm going to write it this way. Sorry, I said sine n minus 1. Sine n minus 2x cosine squared x, right? dx. Go with me? Anyone have any issues with this? Follow? All right, is that the formula? Look at the, well, if you wrote it down, hopefully you wrote it down. Did our formula, was the first piece sine to the n minus 1x cosine x? Did it have those in it? Yes? But it had something else out here, didn't it? It was negative 1 over n? We don't have that yet. Okay, how about that other integral, or the other part of it? Was there an n minus 1 in it? Yes, but it was divided by n. Was it plus or minus? It was plus, so it's starting to look like the formula, isn't it? Over here, what did we have in this one? In the integral? Sine to the n minus 2x, right? But no cosine squared. So it looks like we're starting to get to something, right? We're starting to, but we're actually not there yet. All right, so let's continue. What I'm going to do now is I'm going to work with this. I want everyone to tell me what this is from pre-cal. It's 1 minus sine squared x, isn't it? Isn't that 1 minus sine squared x? So if I rewrite this entire line, negative sine n minus 1x cosine x plus n minus 1 integral sine to the n minus 2x 1 minus sine squared x dx, right? Then that's just replacing that with 1 minus sine squared. And then what would happen if you distribute this through here and here? So what's sine to the n minus 2 of x times 1? Itself, right? What's sine to the n minus 2 of x times that? Sine to the n, right? You add the exponents? Sine to the n. Okay, so let's see what happens here. This equals negative sine to the n minus 1x cosine x plus n minus 1 integral of sine to the n minus 2x minus sine to the what did you say? nx dx. Agreed? All right. Anybody see it? Anybody see it? Anybody see it? What is this? What is the integral of this? It's the original thing. Didn't this happen before? When the thing we were trying to solve for appeared over here? And what do? We moved it back over here. This was the rabbit out of the hat one. Right? So the integral we want actually is over here. So we're going to need to get it and move it to the other side. But to do that, we have to first release it from, right now it's being, you can almost look at this n minus 1 as being a scalar out in front of this, right? So what I'm going to need to do is I'm going to split this into two separate integrals, distribute an n minus 1 through to each one, and then move that one over. Okay? That's what I'm going to do. All right, so now my next line. So what I'm going to do, I'm going to keep this is the original problem. I'm going to rewrite this line right here. Okay, this is where we were, right there. Okay, and this is negative sine to the n minus 1 x cosine x plus n minus 1 integral sine to the n minus 2 x dx minus n minus 1 integral sine to the nx dx. Robert, do you see this? Do you see what I did here? You see the n minus 1 has to go to both? Okay. So I have a minus sign there. So now, let's see. I'm going to add that to both sides, right? This. So how many of them do I add? Yeah, what's the number out in front of it? N minus 1. So I'm going to add n minus 1 of these integrals, right? Like if that were a minus 4, I'd be adding 4, right? Same thing over here. I have to do this to this side. Going to add n minus 1 of these integrals. Right? That's what I'm going to do. It'll cancel on this side. Alexis, how many of these do I have now? How many of them are here? That's how many are here. How many are here? One of them, right? If I take one of these and I add n minus 1 of them, how many do I have? N of them, right? And I'm going to divide by n. Yep. So when I add these two together, I'm really adding these almost like coefficients. Like 1x plus 5x is 6x. But when you add these two together, the ones cancel, you just have the n. So we're actually really close to being there. I have n of these integrals is equal to negative sine n minus 1 of x cosine x plus n minus 1 integral sine to the n minus 2x, right? That's what I've got. And Ron, the last thing, right, you said? Yeah, divide everything through by n, right? Just divide by n now. Divide by n, we divide this by n, we divide this by n. So let's do that. Divide this by n, divide this by n. I don't know, divide the whole thing by n. Divide this one by n, I'll put it right there. And you'll get what? Integral sine to the nx dx equals, now I could just leave this, right, like this all over n. But I could also write it like this, negative 1 over n, couldn't I? Sine to the n minus 1x cosine x. I mean, that's the same thing, right? That's the same thing. And then over here plus n minus 1 over n integral sine to the n minus 2x dx. That's it. That's the formula. If that doesn't get you excited, nothing in this class is going to get you excited. I'm kidding. So when you go and you flip to the back of this book and you look at these formulas that they have here, you know, and you go, where do these come from? You know? It wasn't, no, I better just shut up. I won't go there. I don't want to get political or religious in here. So I will just say that These were not provided to us by any divine power. These formulas came from people who ground them out, right? Had to come up with these. And that's an example of how something that looks pretty ugly, it's doable, right? I mean, there's a little bit of magic in there where how did they know to write that first one to break it up? But I'll tell you how they knew. Someone really wanted to solve that problem, and they just kept beating it to death and trying over and over and over, different things, and finally got something to work. And that's the way a lot of mathematics works. You get these nice, elegant results. You don't realize there's like years and years of pain and suffering that's behind that someone found that. So we just get to reap the benefits of getting to use it. Okay, so that is an example of proving a reduction formula. And there are, I believe, a few of those on your homework. Did I give you those for homework? Let me see. I believe I assigned number all the way up to number 32, right?
35 and 37.
Okay, so, and 31, right? 31. Number 31, number 32, number 35, and number 37 are all reduction formulas. And I challenge you to do those. I did not do a video on those. In my video that I did do, I told you I'm not going to do the reduction formula ones because those are usually bonus problems on a test. So there's a very good chance that one of the problems that I'm asking you for homework will appear as a bonus on the test. I'm just not going to work it out for you. At least you know the answer, right? You'll know what the answer is because it tells you, show this is true. So you'll know what you need to get to. It's a matter of getting there.
So you'll be giving this in the questions?
I'd say prove this. Yep. And then you'd have to do all the work I just did. All right, well, what I've decided to do, all right, is I've decided that due to the quizzes, which were pretty good, okay, the quizzes, there was a good chunk, I'd say 80% of the class got perfect score on that quiz that I gave last time. I feel like hopefully everyone's kind of keeping up to speed. I'm going to give you the weekend to really get that integration by parts down. And then we're supposed to come back and have, what? Our test is next Thursday, right? So we're supposed to come back. Wait, no. Yeah, is it? Yeah. We're supposed to come back and do a review, right? What I've decided to do is to introduce you to this concept and put maybe one or two of these on the test. Now, the reason why is because these, I think, are a lot cleaner and easier than integration by parts. So when you see these will actually be kind of, you might be like, good. You know, like, I feel comfortable with these. Because there's really only so many things you can do with these sorts of integrals. All right? So we'll look at that for the next half hour, 45 minutes. All right, 6.2 is called trigonometric integrals. Didn't I promise you I was going to let you all work together? Like work? Sorry, I lied. So trig integrals and substitutions. This section has two major concepts in it. Trig integrals, which are integrals that have trig functions in them, and then what are called trigonometric substitutions, which are integrals that do not have trig stuff in them, but we turn them into things with trig stuff in them. That's a much more difficult concept. All I'm going to do is work on the first part of this section, which is trigonometric integrals. So we have seen already, we know the antiderivative of sine and cosine, right? We also talked about last class that if you had a linear expression inside of a trig function, right, that we always have to scale by it when we integrate it, all right, but by the a. And now what we're going to look at is a strategy for integrals that have sines and cosines in the integral together. Not just a sine by itself, not just a cosine by itself, but sines and cosines combined. And have some sort of like general attack or strategy for those. So here's the first strategy. And there are 1, 2, 3 strategies for when you have cosine and sines together. Right? The first strategy says if you have cosine to the n power in your integrand and the n is odd, then we're going to use a Pythagorean identity. then we're going to do blah, blah, blah. I'm not going to read through this. When I do an example, you'll see, I'll show you what I mean by all these words, okay? But it's like if the power on the cosine is odd, we're going to try this. If the power on the sine is odd, we're going to try something else. And if you have the power on sine or the cosine being even, we're going to try something else. All right? So those are the things we're going to go for, and here's the first example. So let's do that first one, A. We're going to have integral sine cubed 4t dt. Now I will point out, or I will ask you, Kiki, can you use the reduction formula we just proved on that? I mean, but do you think it falls into that format? What's the n here for us? 3. And so in that reduction formula, the new integral, wasn't it n minus 2? So if we take 2 away from that, it would just be sine in that new integral, wouldn't it? And we can do that, right? So the reduction formula would work very clean on this, wouldn't it? But let's try something to get us used to this new strategy, because if I throw like a cosine squared in here, it's all going to go crazy. You won't be able to use that reduction formula. So according to this, if I have sines and cosines, and my cosine is odd, I do the first thing. But I don't have cosine odd, right? I have the second thing, which is sine is odd. So let's see what this says. If sine is odd, here's what I'm going to do. I'm going to use the Pythagorean identity. What I'm referring to here is this identity. Remember that from pre-cal? I'm going to use that identity. I'm going to factor out a single factor of sine. So I'm going to come to my integral. I'm going to rewrite it. I'm going to factor out a single factor of sine. So I had 3 factors of sine. It was odd. So I'm factoring a single factor out. Everyone agrees that's the same thing? Come on, Kiki.
I'm trying not to die. Sorry. I'll die for you.
Yeah, if you're going to die, please don't bother us while you're dying over there, okay?
I'll try not to put it in you.
Please. Thank you. All right, so once we do that, what? We pull out a single factor. What does it say? Which leaves an even power of sine, doesn't it? Like if this was odd, and I pull out one sine, I'm guaranteed that this is going to be even, right? If that was 5, I pull out one sine, I'll have sine to the 4th here. So no matter what, this should work. Now what do I do with that even power of sine? Rewrite the remaining even power of sine using this substitution. So remember that with this identity, I can always move things around here. So I can just rearrange this sine squared x equals 1 minus cosine squared x, right? I'm allowed to do that? So everywhere I see a sine squared of something, I can replace it with the 1 minus cosine squared of that something. So I'm going to replace this right here with 2 terms. And since there's 2 terms, I need a parentheses. 1 minus cosine squared, Kelly, of cosine 4t. There we go. And then the rest of it, the sine 4t dt. Now, without looking too far ahead, let's see. Matthew? Why in the world would I do something like this? Think back, Matthew, to when the first technique of integration we ever learned, right, was what? I mean, other than after the power rule, we learned the basic substitution, right? Look at this right here. And go back to the good old days when it was just, do I see something in a derivative?
Yeah.
You see something as derivative? What do you see? Either way, right?
Yeah.
If we let this be u, the derivative of it's there. If we let that be u, the derivative of it's here. Which is better? You want to use the one in here. The reason being, because the derivative of it needs to be free from the other stuff. If you let u be sine, then the derivative is in here and it's squared and it's 1 minus and it's in parentheses. You don't want that. You want it free. So this is a pretty good candidate for a u substitution, isn't it? Just a basic one. And that's what this technique tells you. Okay, you've done all the stuff it told you to do. Now, just let u be cosine x and use substitution. So now what I'm going to do is I'm going to make a substitution in the problem. Everywhere I see u, I'll replace it with cosine, now not x, what here for us? 4t. And then now I just go through the basic substitution. The derivative of this is 4 sine 4t dt. Because of chain rule, right? You have to take derivative of what's inside, and so we're off by 4. And so do we have this? Does this appear in our integral? Almost, right? Almost. We've got sine 4t dt. Sine 4t dt. So we're off by a factor of 4, aren't we?
Is that going to be negative?
Yeah. Why didn't I put negative? Is that why y'all were all looking at like that? That's the second time you caught me, Karen, right? You caught me on another one that I left out over here. Remember that a couple of classes ago?
So u is not going to be the 1 minus cosine?
Doesn't need to be. Nope. You actually, if you did that, your derivative would be more complicated because you would have to use the chain rule. So the 2 would have to come out. Like if that were cosine squared, 2 would have to come out. Then you would still have cosine. Then the derivative of cosine is negative sine. So it would be kind of messy.
Why would you use 1 minus cosine?
That's what I'm saying. Watch. If I do this.
I'm not saying you squared, but you have to take it.
Oh yeah, no, you can't because that's not there. This is not here. The order of operations, excuse me, says you have to square this before you can combine these together. So you can't let u be something that would change the order of operations. Like how would you rewrite that? If you're calling 1 minus cosine 4t u, then how would you rewrite this here?
Well, it's because the squared isn't on the outside.
Yeah, if the square were out here, then yes. You following me?
Yes.
Okay. Okay, so the derivative of cosine is negative sine, chain rule, negative 4. So I need to scale by that. So negative 1/4 du is equal to sine 4t dt. Any questions? All right. Paul, you feeling good today? All right, you want to tell me how I can rewrite this integral in terms of u? Can you see it okay? All right, so I'm going to do it up here. How could I rewrite that integral in terms of u? 1 minus u squared, good. And then what's all this? Okay, I'm going to pull the negative 1/4 out here. Du. Good, right? And what's good about that integral? It's so easy, right? This is just basic power rule. What's the antiderivative of 1? U, right? And what's the antiderivative of u squared? 1/3 u cubed. That's it. We're done. And then we have the negative 1/4 out there also. But do you see how that became very clean after we made the substitution? So 1/4 antiderivative of each one. So antiderivative of 1 is u. Antiderivative of u squared, negative 1/3 u cubed, plus a constant. All right, Dustin, feeling good? You want to give me what the answer is, distribute the negative 1/4 through, and replace everything with u. See if you can walk me through what this next line would be. U with what was u? Okay.
cosine, or negative, yeah.
Uh-huh.
Equals cosine 14.
Don't forget, do.
So positive 1%, 12.
Yep. So cosine cubed 4t. Right? That's u. U is cosine, and when we cube it, we like to put the cube there. That's the notation we use, and then plus c. We good? It's a little better than integration by parts, right? Another thing about these is that as soon as you see them, you kind of know what you have to do. Are there any questions on this? Y'all got a question?
Okay, so when, since it was negative cosine 4t as u, wouldn't that change the signs on both of those?
The u was not negative cosine. It was just cosine. The derivative was negative sine. Zach, remember you were skeptical about these last class because like how could the derivative of this possibly be that? On the videos I did a few, I think 2 or 3 just for you, Zach, just to show you that the derivative did work out. So I'll do it on this one quickly, all right? So what is the derivative of that right here? Let's see, negative sine of 4t times 4, right? Negative sine. So what happens when that negative 4 comes out and hits this? You just get what? Sine 4t? That's what you would get when you take derivative of that? Okay. Here, bring the 3 out. I'll do this one a little slower. 3 comes out, it becomes what? 3 over 12 is 1/4. Cosine what? Squared of 4t. Now you have to take derivative of cosine, which is negative sine of 4t. But then you have to take derivative of what's inside, which was what? 4? This 4 and this 4 cancel? Yes? Y'all agree with this? So what do we have here? Is there anything I can do with this? Can I factor out? How about if I factor out? Let me see. I'll rewrite it so it'll look a little more obvious to you. Ah. So I just took that negative and slid it out in front. What can you do here? Factor out a sine 4t. If you do that, what's left? 1 minus cosine squared 4t. But what's 1 minus cosine squared 4t rewritten? It's sine squared 4t. And so you have sine 4t times sine squared 4t, which is sine cubed 4t, which is the original integrand. It worked. Okay. Let's try another one. So for part B, we have integral sine squared x cosine to the 5th x dx. Are we allowed to do exactly the same thing we just did? No, right? Because what we just did is when you have an odd power on sine, right? We can't use the reduction formula that we proved at the beginning of class because that only works if it's just sine by itself, right? So whenever we have sines and cosines combined, we look at these 3 possibilities. And the first case is what you do when you have cosine having the odd power, which we have here, right? So what does it say for us to do? Use the Pythagorean identity again, but this time we're going to factor out what? A single factor of what? Cosine instead of sine. So I'm going to rewrite this. X, hold on, cosine, yes, this one right here, and then I pulled, sorry, dropped the ball on that one, sorry, fourth, and then cosine x dx. So I just left sine squared alone, cosine to the fifth, I rewrote as cosine to the fourth times cosine. This time I'm going to use a Pythagorean identity, but the other way. Instead of using this, right, that's what I used for the last one. Everywhere I saw sine squared, I replaced it with this. Instead, I'm going to use this version, which is the Pythagorean identity solved for cosine squared instead of sine squared. And so everywhere I see a cosine squared, I'm going to replace it with this. Okay? But I don't have cosine squared. I have cosine to the fourth.
Cosine squared plus cosine squared.
That's cosine squared times cosine squared, right? Even better, could I write it like this? Sine squared x times yeah, I'll do it this way. Cosine squared x squared cosine x dx. Do you agree that cosine to the fourth x is cosine squared x squared? Yeah? And now this becomes integral sine squared x in parentheses and squared what? 1 minus sine squared x and then cosine x dx. Ivana? The whole purpose of that is because now you look at this and you see what?
Factoring out
How do you mean factor it out? What I'm trying to ask you is what technique of integration do you see we could use? Just a basic substitution, right? Just a basic substitution here. Because if I let u be what? Sine x, the derivative of it is right there. Sitting there waiting, nice and patient, right? And that's what the step even tells you that at the very end. It says let u be sine x. So these little hints actually tell you exactly what you should use for u. So now I let u be equal to sine x. Du is cosine x dx. And I rewrite the entire integral. And let's see. Who have I not called on? Anyone here want to do it? I know I've called on yo too many times already. Go ahead, Christy. I don't call on you now. Just rewrite this integral with that substitution. U squared 1 minus u squared squared du. Right? Everything just goes clean into it. That's du. This is 1 minus u squared, but then all of that's squared, and then this is just u squared. How are we going to do this, Sean? Or how would you do this, I should say, Sean? At this point, it should be simplified. Like you shouldn't need anything crazy now.
If you take out the u squared, to the front or?
Out here,
Yeah.
be careful. You can never take a variable that's part of your integrand, right? The variable can never come out. You can always pull constants out, but you can never pull the variable itself out. Anyone? Yes?
Separate the squared to 1 minus u squared.
Just square it, right? Just square it. If you square that, you get a bunch of powers of u, don't you? Then you just distribute a u squared through, and then you just get a bunch of powers of u, and then you just do power rule on each one. So at this point, it's just some algebra to clean it up. You don't have to use any crazy other techniques. So this is integral u squared. When I square this, I get 1 minus 2u squared plus u to the 4th du. So I'm just doing that mentally. This times itself, FOIL it out, collect like terms, you get that. Agree? And now just distribute the u squared through. I'll have 3 terms. U squared minus 2u to the 4th plus u to the 6th du. Alejandro, you want this? Not really? Just apply your power rule to each one. I'll put this in.
It's going to be 1/3.
Oh, no more integral, sorry. Yeah, 1/3.
U to the 3rd power.
Uh-huh.
Then minus, is that 2/5?
2/5.
U to the 5th power.
Uh-huh.
Plus 1/7 u to the 7th
Yep.
power. And plus 2.
That's it. And final step, replace all your u's with sine x. So this should be 1/3. It's sine x, but then being cubed, so I'll put 3 here. Then it's minus 2/5. And then it's sine x, but then raised to the 5th. And then plus 1/7, and then sine x to the 7th plus c. That's it. I won't check this, Zach, sorry. Not going to do it. What I think is worth mentioning to you is that if you go to Wolfram alpha and you say integrate, what was it, sine x squared times cosine x, was it to the 5th? Yes? Okay, if you ask Wolfram alpha to integrate this, oh, wow. Did we mess up? No, it's just that Wolfram alpha did additional things. What they did is they said, okay, I'm going to use some power reducing formulas on this. Because notice your angles have changed there. They have a sine cubed x in there, don't they? But they've got a bunch of other stuff. They've got a cosine 2x. Do we have a cosine 2x in here? Somehow they changed things into double angle formulas, and they actually have a cosine 4x, so they applied double angle twice. So I always know, like on a test, when students use like their TI-89, things like that, because your calculator is going to do more than you would do. You would stop here. So if your answer has like cosine 2x, you obviously didn't do it, right? Because to get it to look like that is about another 30 minutes of work. But this is correct. This is a correct antiderivative. That's just identities to get it to look like that. So be careful. All right, that's fun. You want to do another one? This will be our last one. Cosine to the 4th x. This is sometimes referred to, in my mind, beta t, sorry. Cosine to the 4th beta t dt. In my mind, this is considered to be, an instructor that puts a problem like this on a test, it's considered to be torture, okay? Because this is very tedious, this problem right here. Now, there is a formula that we could use in the back of the book. You know how we had one for sine to the n? There's one for cosine to the n. But let's try not to use that formula because you can't use that on your test. Let's try and do it using technique here. So remember, the first two little techniques were what you did if cosine was odd or sine was odd, right? The third one, which we haven't discussed, is what you do if either one of them are even. And in this case, we only have cosine, and it's even, right? It says here, with this, we're going to use the half-angle identities or the power-reducing identities. And these are from pre-cal. And the two identities are written right there. And I'm going to write them up here just so you see them. Sine squared x equals 1 minus cosine 2x over 2. Anyone recognize that formula from pre-cal? We call this the half-angle or power-reducing formula. The thing that's good about this formula is that it allows you to take a trig function like sine that is being squared and rewrite it where there's no more squareds. But there's a give and a take. You lose the squared, but what do you gain? A double angle, right? You double the angle. So that's a formula. Now I have it written in a different way here. I have it written where I pulled that 1/2 out of everything. Right? That's the same exact thing. Or you could split this into two fractions and go 1/2 minus 1/2 cosine 2x. All three of these are equivalent, right? They're all the same, and you can use any of those versions when you're doing this problem, right? There's another identity for cosine squared. And what's the difference between the two formulas? There's only one difference. Addition. If this was cosine squared x, this would become a plus, a plus, a plus. That's the only thing that changes. All right? So you ready to use those? Yeah? Come back to this. What does it say? If you have this even power, then you just use the formula. It doesn't tell you anything else. So let me try and rewrite this. I know that anytime I have a cosine squared, I can use this formula with pluses, right? So I need to first realize that I do have a cosine squared. I have a cosine squared beta t, what? Squared dt. Yes? That's what I have. Now, I can now replace cosine squared beta t with any of these. So I like to use this one. All right? The reason I like that one is because I can pull the 1/2 out at some point. So do you agree with this? I'm going to leave those formulas up there so you can refer to them. You'll realize, since this is the only example I'm going to do, you'll realize I'm using this right here, right? That's the one I'm using, right there. Okay. So this becomes integral in parentheses. Ethan, have we talked today? Ethan? Okay. So use that formula. Tell me what this is going to become.
Kind of replacing
Oh, wait, I circled that one. That's not the one I want. Damn it. Sorry.
using the first.
I want this one. Sorry, I wanted this one. That's the one I like to use.
Okay.
Okay.
Awesome.
So in that parentheses, what do you want me to write?
Putting 1/2
Okay, 1/2.
and starting another parenthesis.
Another parentheses.
1 plus cosine
1 plus cosine
of 2x.
of
2x. Or beta t, say
2 beta t. 2 beta t. Shit. Hold on. Okay, got to make sure I get my parentheses right there. 2 beta t is inside the cosine. 1 plus cosine is in parentheses. There's a 1/2 in front of that. All of that's being squared. Yes? So no matter what the argument is, right? The argument's the thing in the function. You're going to double that argument. So if it's beta t, it now becomes 2 beta t. All right, now let's actually do some cleaning up here. When you have something raised to the second power and you have multiplication, right? You can actually just square this one and square this one, right? So when I square 1/2, what do I get? 1/4. I'm going to pop that out of the integral now. So this becomes 1/4 integral. But I still had all the other stuff. 1 plus cosine 2 beta t, all of that quantity squared, dt. All right, who's up to bat? Ruben, we already did something, yeah? No, not today? Not today? You feeling up to it? Or Vanessa, you feeling up to it? All I want you to do for me right now is actually square this. I want you to do FOIL on this. So, write it side by side and do your little FOIL game, and let's see what happens. I have 15 minutes. What are you getting anywhere? So, first thing is what? 1 plus another, so 2 of them, 2 cosine of 2 beta t, right? Plus cosine squared of 2 beta t, right? dt. And we had a 1/4 in front of all that. All right, now take a look at what you have, all right? Take a look at this. I know that that looks pretty nasty, but let's just take a step back. How many terms are there in this integral? 3, and since there's 3 terms, we could look at them separately. Can you tell me what the antiderivative of 1 is? T. What's the antiderivative of just a cosine function? It's going to be a sine function. I'm going to have to take care of some of the constants there, right? This one? Not so much, right? But guess what? It's cosine to the 2nd power. That's even. I can do that. Again. You see what I'm saying? And that's what you have to do. So let me just go a little bit further. For integral 1 dt plus 8 integral cosine 2 beta t dt plus 1/4 integral cosine squared 2 beta t dt. So I've split this into 3 integrals. I've taken my 1/4 through to each one. Oh wait, why did that become an 8? I have no idea why I put that as an 8. That should be a what? 1/2? Sorry. 1/4 times 1. Why did I do that? What the hell? I'm having like brain spasms up here or something. What? I am pretty eager to leave. But try this again. All right, 1/4 times 1, 1/4. I'm integrating 1. 2 times a 4th is a half. I've got the cosine here. This times 1/4, at least I got that one right. And then cosine squared 2 beta t. Let's go ahead and find these antiderivatives. We just said that this one would be 1/4 t, right? Okay, now Ruben or Vanessa, I'll give you another shot at this. Forget the 1/2. Antiderivative of cosine 2 beta t. Vanessa? No? No? Okay. Anyone at that table? Kelly? Is it negative sine? You're taking the antiderivative. Sine? Okay, sine of 2 beta t. But what about the number that's in front of the variable here? Don't you have to scale by that? So 1 over, okay, look, so here's a 1/2. I've got to scale this by, everyone now? 1 over 2 beta. Beta is a constant. 1 over 2 beta sine 2 beta t. That's the antiderivative. Agree? And then over here, plus 1/4 integral. I can't integrate this yet, right? I can't integrate that yet. But I can use the power reducing formula again. And this will become 1/2, then in parentheses, 1 plus, right? 1 plus cosine of 4 beta t, because you're actually doubling what's in there. So this becomes cosine 4 beta t, and then dt. Understand? Now, how many terms do we have here? 2 terms. Can you integrate each one of these? Yes, antiderivative here, antiderivative here. So one more line and I should have the answer. Well, maybe what I should do is, to help you out here before I write it, let me pull the 1/2 out, 1/8 integral, and what's left here is 1 plus cosine 4 beta t dt. So I just pulled the 1/2 out. So here's going to be my last line, and I'm going to actually integrate that, and I'll be done. So equals 1/4 t plus 1 over 4 beta sine 2 beta t plus, okay, right here, antiderivative of 1 is t, so 1/8 t. What's the antiderivative of this? Negative? Careful. It's going to be sine of this, right? But what do I scale by in front? 1 over 4 beta. But what was in front of the whole thing? 1/8. So 1 over 8 times 1 over 4 beta is 1 over 32 beta plus 1 over 32 beta sine 4 beta t plus c. We're pretty much there. Here's one more thing we could do. I have 1/4 t and 1/8 t, and I could turn that into what? 3/8 t. I could put them together. Other than that, I'm done. So if the problem had been presented to you in the very beginning as a cosine squared, we only had to use that power reducing formula one time, right? But the original problem was cosine to the 4th. So how many times did we have to do power reducing? Twice. What if it was cosine to the 6th? You would have to do it 3 times. And I've seen people do that before. I've actually seen instructors give like cosine to the 6th on a test. And it's just like, exactly why. So let's have a little heart-to-heart here, all right? Because I do have a couple more minutes. You all know already that math is one of those things that always grows on itself, right? It's always, you take college algebra and then you use that somewhat in pre-cal and that's somewhat used in calculus. We know that already, that math is like a pyramid, right, that you build up on. If there's holes in your math, then it's hard to build a pyramid. Cal 2 is really, no class you've ever taken builds on itself faster than this class. So like when I'm going around the room and I'm asking you to, and I'm not calling anyone out here, but I have a concern Okay, Ruben, Vanessa, I have a concern. I don't want to call you up, but I have a concern because this right here has to be mastered by the next time we meet. And that was from last class. That has to be mastered. You have to be able to integrate this. The next time we meet, that's the expectation. That's what I mean by it builds on itself so fast. Everything we just did right here, okay, this problem right here, cosine to the fourth, will be what we try and get to next class. We're going to have an integral we can't do, and we're going to get it to cosine to the fourth and be like, yes. Because once we get it to cosine to the fourth, we can do this. That's going to happen not a week from now, not 2 weeks from now, next time we meet. Understand? So it's everything coming so fast, you have to keep up with it. There's no time to go and say, you know what, I'll just, before the test, I'm just going to do all my homework. I'm going to go through. It has to be happening in a steady, what do you call it, like constant applied pressure. It's not a sprint, it's a marathon. You got to be, am I making sense? So anyone that I'm calling on and I'm not getting the responses, there's room for concern there. I mean, you should do something about that. Or if you're sitting there and you're like, please don't call on me, please don't call on me, please. If you're just like mentally thinking that, that's why I'm doing it. Because I want you to know if I feel like you're not where you need to be. Understand? It's a weird technique because I've never done this before. I've actually called people out, but I need to know where you are. It's hard for me to look and just be like, yeah, they get it, they don't, they do. It's impossible. So I need to get feedback. All right, so y'all know what to do. Do your integration by parts homework. Let me give you a few problems from this if you want to get ahead a little bit. Why don't you look at page 326, and let's just look at (1 through 13) odds. That'll just kind of get you started with these trig integrals. What we still have not touched yet, which we will have to touch next class, is what if you have tangents and secants mixed up, right? Or just secants by themselves, or just tangents, or just cosecants. And so we have to use, remember the Pythagorean identity, there were 3 of them. Sine squared x plus cosine squared x equals 1, but there was another one. It was like 1 plus tangent squared x equals secant squared x, and then there was another one. There's 3, so we can actually do that same sort of thing with other trig functions. So we'll do that, but that'll get you at least started with the sines and cosines. Everyone have a great weekend. I'll see you on Tuesday. If anyone wants to talk to me, right. We're waiting for that projector to get fired up there. The class average on exam 1 was 70. The standard deviation was 15 points. So if you know anything about statistics, that means that if this was a normally distributed bell curve, if it was, then the class average was 70. And the distribution of the grades was something like this. Most people would lie within, 15 points of 70. And almost everybody would lie within 30 points of 70. So usually 2 standard deviations out is, if you're outside 2 standard deviations, then you're an outlier, which means you're either exceptionally on the high end or exceptionally on the low end. So take 70, subtract 30, and that's a 40. So if you're under a 40 on the test, that would mean that's exceptionally far from the class average. Or if you were 100 or higher, that would be exceptionally high. Make sense? All right, so the grades were, I've got a little summary here. We had 2 A's, we had 8 B's, we had 5 C's, 5 D's, 5 F's. And then if you actually look at the grade distributions, let's see here. Oh. The highest grade was a 99.3. And so you can see here the 2 A's and then the B's. So we had a couple of very high B's, almost in the A category. And then you had, these are all B's, and then we dropped to the C's, the D's, and then the F range here. So I think there would be reason for concern at this point. I think the break point would probably be here, right about there. Anything to the right of that, if your grade was to the right of that, I would just be a little concerned. You know, you're going to have to change the way you're approaching the class, the time you're putting into it. You know, if you've always studied a certain way and this is the result you're getting and it's not what you want, you've got to adapt, all right? Make a change. Now, these were the raw grades, so I did no curving or anything like that. I know that the test did run a little long, so I have another set of data where what I did is I went to each student and I dropped each student's lowest problem. I believe I have it. Where's my summary? And those are the grades in order. I can't find, I had a spreadsheet of what I did is for each student I went through and said how many got counted off, like for number 1, each student, and how many points I took off for each student. And from that I was able to figure out what problems were most commonly missed. And it wound up being the ones at the end, and I think it was just a time thing. So I haven't decided yet how I'm going to do it. I think if I change it where I drop your lowest problem, it benefits most of you. I think there's 2 people where it actually hurts them if I drop the lowest. I know that doesn't make sense, but that's what happens. And then the class average goes up to a 74 if I do that. So I'm considering that. I'm not locked into it. I actually haven't looked at this since I graded them, which was Friday? I think Friday morning I had them done. So, any questions? Your grade is on the bottom right-hand corner of the second page. Okay. For the most part, I mean, I was pleased with a lot of what I saw. A class average of a 70 on Cal 2 exams pretty good. I think it's not bad. I don't make exams to try and get a certain class average. If everybody in here was capable of getting 100, I wouldn't make the next test harder. You know what I'm saying? These are the same tests I've been giving for too long, all right? And so I haven't really changed anything as far as difficulty. I won't ever change that for the class, if that makes sense. I won't make it any easier. If everyone's struggling, I won't make it any easier, but I'm not going to make it harder if everyone's doing well. So, no questions or comments, concerns? All right. In that case, we'll get back to the material. So hopefully you remember, Vanessa, do you mind hitting the lights again for me, please? Just turn them on. Yeah, thank you. Hopefully you remember that the last time that we were talking about things, we were in chapter 6, section 2, and I told you that there were really two parts to this section, what were called trig integrals and then trigonometric substitution. And there's a process for these, and I hope that at least when we did them in class that day, it seemed like y'all liked them. I don't know if the test reflected that so much, because everyone freaked out on the cosine squared one at the end, which was my idea of giving you a nice problem, you know, that would be quick, easy credit. That's what my goal was, but it didn't quite work out that way. A lot of you tried integration by parts on that, and it was a disaster. But anyways, we are going to finish up the first part of section 6.2 and begin the second part of section 6.2. And there's a lot of information in this section as far as techniques and strategies. So what I did is copied and pasted those techniques and strategies out of the textbook, and I've printed them out for you. So please take these and pass them around. I still don't know if you'll be able to use this on the test, your next test. I doubt it, but at least while you're doing your homework and you're getting acquainted with the material, you'll have something to go off of. All right? Y'all okay?
Who got the 99?
I can't tell you.
Just curious. I was just wondering.
No. I thought it was you. Wasn't you? Oh. You know, normally when I have, I'll tell you this much. Normally when I have a Cal 2 class, I always have students who have taken Cal 2 before, like they've seen it before. And a lot of times it'll be that student or someone who's seen it before that does the best on the test because, you know, it's their second time through. I can tell you the student who got the highest grade, this is their first time seeing Cal 2. So that much I can say. Okay, let me shut up and start getting back to the notes. So we had tackled problems, if you recall, that involved sine and cosine mixed together within an integrand. And we tried to address how we do that. And there were basically three techniques, and they are now here on this sheet on the top left-hand side. It says how to integrate powers of sine and cosine. You see that? It has three different strategies. Now what we're going to do is look at the column to the right of that. It says how to integrate powers of tangent and secant. That's where we are in the notes. There are two antiderivatives everyone here should just be automatic with, and that's secant squared and secant x tangent x. So we should all be comfortable with the fact that if we're ever looking at the antiderivative of secant squared, we learned from Cal 1 that that's tangent x dx, right? Or tangent x plus c, right? We're all okay with that. And the other one was if we ever had secant x tangent x, that's just secant x plus c because that's the antiderivative, right? That's the antiderivative because the derivative of that is that, right? What if you just have in an integral tangent x, or if you just have in an integral secant x? Do we know the antiderivative of those? They're on your table though, right? if you look at your cheat sheet, you should have the antiderivatives for all the trig functions that are raised to the first power. You can double check it yourself. You should see the antiderivative of sine is there, the antiderivative of cosine is there. Is the antiderivative of tangent there? What formula is it? Formula 12? It's kind of ugly. How about the antiderivative of secant? Formula 14? Antiderivative of cotangent by itself? Where's that? Oh, 13. Y'all see that? In your formulas, if you ever have any of the 6 basic trig functions by themselves, you're good to go, right? But these are special because these came from Cal 1. They are the derivatives of tangent and secant respectively. All right, with that in mind, we also need to remember that when we have a linear expression and function, remember when we integrated and we had a linear expression, we always had to scale by that a, the 1 over a in front, 1 over a in front, 1 over a in front. Okay, let's just keep in mind that we need that also. And then let's look at this technique. So I have the strategy up here, but I'm going to look at these 2 examples. With the secants and the tangents, there are only 2 strategies we have. The first one says what to do if you have the power of secant being even. The other strategy is what you do when the power of tangent is odd. All right? Those are the 2 strategies. I give you 2 examples. Each example is an example of one of those strategies. And then I've done a lot of the homework for this section. I have not finished it. If you watch the video from of me doing the homework out of this section, when I get to secant and tangent, there's quite a few examples that I do with different variations of those 2 techniques. I'm falling a little bit behind on trying to keep up with the homework with the videos. I've probably put about, I don't know, 3 or 4 hours into this assignment so far out of this section. And I'm still not done with the first half of the problems. So my plan is tonight I'm going to go up into my attic. I'm going to dust off my old 4x8 whiteboard. I'm going to put it up in my office and make some videos at home. I've been trying to do them here at work, but it's just not possible. So I'll get up to speed. All right, so we take a look at this. We see secant and tangent. We automatically start thinking this, right? We want to also make sure we don't have just like a real basic substitution. I don't see anything real basic, do you? Something that's derivative right away? No? But we do have a secant to an even power, don't we? And because of that, the technique says to do what? I'm going off of the handout. Karen, did you get it? You got one? Okay, well, I have them right here. What does it say? We're going to save a factor of secant squared. What do they mean by save a factor of secant squared? Peel it off, right? Peel off the factor of secant squared because this is all multiplication. Right? I'm going to peel off a secant squared factor. Here it is. And then I'm going to use a Pythagorean identity back from pre-cal that said that secant squared theta, secant squared x they use here, equals 1 plus tangent squared x. You remember that from pre-cal? It's in your formula sheets also. And that identity allows me to, anytime I see secant squared, switch it to that. Now, why is it that they want us to peel off a secant squared? Secant squared is the derivative of what? That's the derivative of tangent, isn't it? So if I make a substitution in the problem, which they tell you here, but I'm trying to get you to think about it. If we make a substitution that u is going to be tangent x, there's its derivative, right? Doing a basic substitution. So du here, secant squared x dx, would allow me to begin to rewrite the integrand. Do we all agree that the secant squared x dx is du? Right? So I've got this taken care of right there. That's going to be du. How about the tangent to the fourth? What's that going to be? That's going to be u to the fourth. So I've got that taken care of. The only issue I need to deal with is the secant squared. Right? Secant squared, though, is that formula I just erased, right? And it allows me to switch the secant squared in terms of tangent, which means basically I can switch this in terms of u, because u is tangent. So this is the only part of the problem that's causing an issue. Why do I know that this is that I'm always going to be able to use the formula secant squared equals 1 plus tangent? How do I know I can use that formula? Because it's even, right? We said it was even to start with. And so if it's even to start with and I peel off a secant squared, this will still be even, won't it? Now, it may not be here, depending on the problem. If there were only two secants and you peel those off, then all that you would have was the tangent anyway. But guaranteed that that's going to be even. So using that identity, I'm going to rewrite the problem. Here we go. This is tangent to the fourth x, replacing secant squared with 1 plus tangent squared x, sorry. And then secant squared x dx. How are we going to rewrite it now? In terms of u. Yep. So we've got what? U to the fourth, 1 plus u squared, and then all of this, du. And that's just a polynomial, right? Distribute your u through, power rule, and we're done after we switch everything back. So u to the fourth plus u to the sixth plus c. I'm already integrating. What the hell? It's not right. Integral u to the fourth plus u to the sixth du. And that's 1/5 u to the fifth plus 1/7 u to the seventh plus c. Any questions? We okay? And last thing would be replace all your u's with tangents. So I'll write this one out. I think in the next problem, once I get to here, I'm going to stop and just assume you could do the rest. But just to make sure we're writing this properly, this will be 1/5. I need the u to the fifth power, so that's tangent x to the fifth power. So we put the 5 there, right? And then we do 1/7, and then we do tangent x again, and then to the seventh, and then plus c. Box it up. That's it. We good? Okay. Now, I'm just curious. I want to just do a slight adaptation to the problem. What if this secant had been secant to the sixth power? Then when I peel that off, what would have been here? 4. And then this could not be this. Right? What we would have to do is the following, and I do this on one of the homework problems, but I'm just kind of pointing it out now. Secant to the fourth x is secant squared x squared, right? So I would be able to rewrite this as secant squared. Where is it? I erased. Oh, here we go. This right here is secant squared, isn't it? But then I would have to do what to this? Square it here. And then that would change this to what? Squared here. And then could you distribute that through? Right here? Not yet, right? What would you have to do first? You have to multiply all that out, then come with your u to the fourth, and then do it. Okay, so that slight little change right here would make a difference in that part right there. Understand?
Yes.
Okay. All right, next one. On the next example, we're doing part B here. We have tangent to the fifth secant cubed. So can we use the first technique again, of peeling off a secant squared? No. That's not what it says we should do. It says if what? Tangent is odd, right? If tangent is odd, I should do what? peel off a tangent x and a secant x together. So I have tangent to the fifth x secant cubed x dx. So I'm going to peel off a tangent and a secant, right? That's what the technique says. So I peel off, here I go. Tangent to the fourth x secant squared x, and then I'm going to put here secant x tangent x dx. See how I peeled one tangent and one secant over here? And then I know that this right here is the derivative of what? Secant. So that's going to be what I use for u. U is going to be secant x because the derivative of it is secant x tangent x dx. So let's see here. You need to start calling some names. You're doing a great job bringing your name things with you, and I'm not calling you on y'all. I need to start working on that again. So let's see. We'll start at this table over here. Any volunteers? Any Cowboy fans here? No? Alexis, are we not talking Cowboys today? No? Okay. You don't like the Cowboys anyway? Okay. All right. All I want to know here, anyone on this table, is how I can, what part of this can I rewrite in terms of u, and what part of it do I still need to address? So like,
Secant square is going to be your u, and this is
okay.
going to be your du.
So you got these two pieces. What about that? What does the technique tell you anything else in there? Anything about a Pythagorean identity in that, or no?
Rewrite it to secant squared minus 1.
Says something about tangent squared. Yeah, so remember that Pythagorean identity that I had up here a second ago? That's what we used in the previous method, right? But if you keep tangent squared here and you move the 1 over, it's a different identity, right? It's the same equation, just looks different. So that's the same thing, right? So that means anywhere you ever see a tangent squared, you can replace it with secant squared minus 1. So we were saying the tangent squared is like, what do we do with it? Well, we're going to look, tangent to the fourth, what do we do with this? This was good, you said this was good. This one we have to work with. So write it as
Tangent squared x to the second power.
to the second power. So if we rewrite this as tangent squared x squared, and then just rewrite everything else, don't even worry about this. We've got this taken care of. Then, let's see, we'll go to the next table now. Any volunteers over there? Where? Nope, just secant. We're pulling a single secant.
Well, now you can put secant squared x minus 1 into.
Yeah, well, yes, that's right. We want tangent squared x is going to be secant squared x minus 1. And if you do that, then everything is in terms of u, isn't it? Because u is secant. So replacing that, I'll do it up here. Replacing tangent squared x with secant squared x minus 1, and then it's squared, right? It has this squared on it. And then the next one is secant squared x. And then I have secant x, tangent x, dx. Okay, I'll give my table another opportunity here since. Sorry. So so you want to tell me what it's going to be then? Hold on, give me a second to erase this. It's still an integral, right?
Yeah.
Okay, so what's it going to read?
U squared minus 1
Okay.
squared.
So the way you can say that, because we run into this a lot of times, you say u squared minus 1 quantity squared. So it gets a little weird because it's just language. I understand what you mean, but just to help you out. All right, so u squared minus 2 unit, u squared, shut up, Robert. U squared minus 1, that quantity squared. All right, and then this right here? U squared times u squared. And then this whole thing is du, so du. And now this is where I'll stop. So I'll say equals dot, 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 meaning you could do it the rest of the way. You would expand that out first. FOIL, right? This is not u to the fourth minus 1. It's not u to the fourth plus 1. This is u to the fourth minus 2u squared plus 1. Then distribute the u squared through. Then integrate power rule. Yes? Y'all are looking at me. Yes or no? Because I can do it if you want, but we're okay? All right. All right, so that's basically the gist of this whole method. It required this other technique, right? All right. There are some other cases, though, which are not so obvious, like these. Now, the first one and the second one are formulas, aren't they? The first one, the second one are formulas. You actually know what those are because they're formulas in the book. I'm going to show you how the first one comes about. It's really kind of easy. The second one, part B, much more challenging and very difficult, actually. The book explains how it's done, and it's not easy, but I'm not going to do it, all right? Because the book explains it. And you have the table. If you were ever on a test and had integral of secant x, you go straight to your formulas. That's what you do. But let me just show you how they get tangent, the formula for tangent. What should my answer be? Formula is formula 12. Natural log secant u, right? That's what I should get? Or natural log secant x here. So here's what I do. I'm going to turn it into sine x over cosine x. That's tangent. Anyone have an idea what to do with that?
Split the 1 over cosine x to secant x.
You want to do
Sine x times secant x.
You want to do sine x times secant x? I could do that. I'll write it down. That's true. I could do that, right? But this has secants and sine. It doesn't have secant and tangent, right? All right, so just clear your mind. Sometimes you have to do that. What's that Office Depot or Office Max? You have that cheesy, what is it? Staples? Oh, Staples, I was wrong. Easy button. Oh, it's not a reset button? Well, then forget it. Just imagine a big red reset button, okay? You reset, wipe the hard drive for a second. No, don't wipe the hard drive. Just wipe the, the RAM, the cache, whatever. Start over. Basic substitution. Do you see something in its derivative? Okay. U is cosine x. Du is negative sine x dx. Do you see its derivative there? Yeah, it's up top, right? Oh, that's perfect. That's what I needed. I just need to take care of that negative, so I just put the negative on both sides. All right, so according to that, this integral turns into integral, but it's really like 1 over cosine, which is 1 over u. And then the sine x dx is really what? Negative du. So put the negative on the outside. Du. Y'all see it? All right, what's the antiderivative of 1 over u? Natural log, but there was a negative out front, right? So negative natural log absolute value of u plus c is my antiderivative. What's u? Cosine of x. Is that formula 12? 12? No. What's formula 12 say? It's not a negative natural log, is it? It's positive. So what did they do? I've warned you about this before. They put the negative up here on the cosine as a power, and then it made that cosine to the negative 1 turn into 1 over cosine. And 1 over cosine is secant. So that's how you get that formula. All right, that's how that one's done. Like I said, B is tough. Really, B came from, I don't know, just look at it in the book. They multiply by 1. They take secant x and they multiply it by 1, but it's a really, really clever one, not something that you would ever really think to do. And it's just someone figured it out that it would work that way. All right, but I will look at this last one here. Secant cubed x dx. So does this one fall into one of our methods? How to integrate tangent and secant. The first method says if secant is even, you do something, right? Do we have an even secant? No. It's not even, is it? So it doesn't look like that formula is going to work necessarily, right? Well, according to that, it won't work. So let me just show you this one, all right? And so, while I'm just setting this up, maybe someone can show me, or can look, is this a formula in your formula sheets? Is secant cubed on there or not? It's not on there? Okay. That's a hint of what I'm about to do. Right? Integration by parts. Now, I'm not going to do anything too crazy. Just think real quick about your dv choice and your u choice. You've got to be able to take the derivative of something, right? And you've got to be able to integrate something, and it's got to come from secant cubed. Any ideas? Secant for u, and secant squared x dx for dv, right? Because you can integrate secant squared, and you can differentiate secant. Perfect. Yes?
I have a question.
Yeah.
Going back to secant squared, can't you take a secant out, turn it into a 1 over cosine?
Mm-hmm.
You would have a secant squared?
Yes, but you wouldn't have the tangent that you need. So you're saying to refer to this method? Like if you wanted to try and create an even secant?
Right.
Yeah. It's kind of cheating because you're just rewriting secant a different way. That's all you're doing. You're not really changing the fact that it is an odd power of secant. Do y'all see this stuff? Okay, so let's fill out the table. What's the derivative of secant x? Secant x tangent x, right? dx. And then what is v going to be here? Go up. Tangent squared? Or tangent? Tangent x. Okay. We all right with that? All right, so this becomes ultraviolet minus voodoo. Secant x, tangent x, minus integral secant x times tangent squared x. And it doesn't appear that that got any nicer, did it? Does that appear that that got any better? But what?
So you get tangents.
You get tangent squared. Pythagorean.
I wouldn't do anything.
Does this fall into our methods? No, because the method said if secant was even, we had something to do. If tangent was odd, I don't have that. So it looks like we got ourselves into a bind here, doesn't it? Appear that way? What I'd like to do, though, I did hear this, the Pythagorean identity, right? What is tangent squared x? Secant squared x minus 1, right? So just follow me here. This is going to be equal to secant x, tangent x, minus integral secant x. And then you said this was secant squared x minus 1? Is that right? Do you see what's going to appear over on this side? What? Secant cubed? Isn't that what we're trying to solve for? Didn't this happen? This was the rabbit out of the hat one. The secant cube is going to appear again, but something else is about to appear. Another secant, right? But they'll be separated. That's right. And do we know the antiderivative of secant by itself? it's part B, which I'm waving my hands at. I'm telling you it can be done. We're just going to use the formula for it, all right? All right, so let's continue. And since I know where this is headed, I'm going to go ahead and write the next line with the left side here, because I'm going to have to add on both sides. So I have integral secant cubed x dx is equal to secant x tangent x, and then distribute through here, I get minus integral secant cubed x dx. And then when I do the next one, I get a plus. And notice also I'm going to split it into two separate integrals. I could do them all in one integral sign, but I'm actually splitting it into two. Because I know what I'm about to do with this one, right? While I'm here, what is the antiderivative of secant x? Formula 14. Is it nice? Not really. This is going to be natural log secant x plus tangent x, isn't it? All right. So I've got that this integral, secant cubed, is equal to secant x tangent x minus the integral that I want, again, and then plus this integral, which is this. So what do I do now? Remind me, I forgot. Going to add that integral right there to both sides of the equation. And I do it over here also. So how many of them am I going to have on the left side? Two of them. Going to have two of the integrals. Yes.
Question.
Yep.
The plus integral secant x and the other integral, do those need to be in brackets?
And the other.
Together or in parentheses, like behind the negative?
I think I already distributed the negative.
Because it was going to be minus.
Because
Okay.
it was secant squared x minus 1,
Okay.
and I distributed the negative to both, and that's why this is a plus. Got it? Okay. I'm glad you're watching me, though. All right, so where am I? This side is what, two of these? And then over here, this is still secant x tangent x, but then what? Over here? Plus natural log secant x plus tangent x. I'll go ahead and say plus c now, all right? And what would be left? What's left for me to do here? Divide both sides by 2. So I could put the whole thing over 2, or I could move my equal sign over, put a 1/2 in front, and slap a big parenthesis around it like that. So I'm just multiplying both sides by 1/2. Do I have to do 1/2 on the c? No, because it's still a constant. It doesn't matter. That's it. The antiderivative of secant cubed is that. All right, we good? We are done with trig integrals, integrals that involve trig functions by themselves or mixed together, sines and cosines, secants and tangents. And now we move into the next topic, which is called trigonometric substitution. This is by far the harder of the two that we are looking at in this section. But everything we just did, okay, everything we just did with all these trig integrals was for a reason. You must be able to do this in order to do what we're about to do. All right, so let's talk about trig substitution. What does that say? After we what? Master. What does that mean? After we master the above concepts, we can use them along with an interesting type of substitution to find more antiderivatives of rather complex functions. These new types of substitutions. So you know how we've done substitutions in the past? We've said like, oh, I see something in its derivative. And we said u is equal to something, right? We've done that? We even used another type of substitution. It was integration by parts, where we let u be something and then dv be something else. So we've done different types of substitutions. This one is very different because it's not something you would think is going to get us anywhere, but it does. So these new types of substitutions we're about to do are called trigonometric substitutions, or as I'll refer to this technique as trig sub, right? Trig sub. The general idea is, and I'm going to read through all that, or I don't want to read through all that. Let me just explain in layman's terms what I'm saying there. If your integrand, that's the thing in here, involves one of these three expressions, there are three expressions. If that integrand has a square root of a squared plus u squared, well, hold on, what do I use on here? X squared, okay. X squared, square root, let me go in the order that they appear on this sheet. A squared plus x squared, or square root of x squared minus a squared. These are three different radical expressions, right? Where you have a constant squared, which is just a number, right? So you have like maybe 9 minus x squared, or maybe 4 minus x squared, or 25 minus x squared, or 3 minus x squared. It doesn't matter. This doesn't have to be a perfect square. It's just a number minus the variable squared. Underneath the root, if that appears anywhere in here, trig sub is what we're thinking. Trig sub. If you have the constant squared plus instead of minus variable squared, trig sub. If you've got the opposite order, variable before the constant, subtraction between them, you're thinking trig sub. All right? That's what gets you started. You have to see this in the integrand to be able to use it. Now, once you've actually determined which of the three it is, each one of these requires a different sort of substitution. So I'm going to go right to this problem right here, all right? Because this is an example of this first one being used. And I'm going to run through the process with you, and I'll refer to these notes once I start doing it. Are you all ready? I was hoping more for like the big huddle, everyone in the center. Are you all ready? The response I got there wasn't quite what I was. No. Okay. Clear the RAM. Basic substitution. Do you see something in its derivative? X cubed's derivative is in here, right? But see, it's trapped. It's a mess in there, right? We don't want the derivative of that being in there. How about the derivative of the whole thing in here, 16 minus x squared? Derivative of that is x, not x cubed, right? Unless you peel an x cubed apart, you might be able to do this, right? Maybe? So there might be a way. There might be a way with another technique. But isn't this also perfectly in that form that I said trig substitution is all about? Doesn't it have this somewhere in the integrand? Yes, you have that, don't you? Now, let's actually write down what we have. We have 16 minus x squared, which means that the 16 is 4 squared minus x squared, which means that the a for us is what? 4. So we have an a being 4. Agreed? All right. So what does this thing say I'm going to do? So reading this table, the way this table reads is the left column says, what expression do you have? Well, I have this expression, right? The next column says, what is the substitution that you would need to make? So what is the substitution that this is telling me I need to make? It's telling me that I need to use what? X is equal to what? A sine theta. Yes, x is equal to a sine theta. For us, what is a? 4. So we're really going to be making a substitution, x is equal to 4 sine theta. Now think about this for a second, what this technique is saying. It's saying you've got this thing in here and you're kind of having a little bit of trouble with it, right? Can't quite get it to work out. So they want you to come in here now, and everywhere you see an x, they want you to replace it with 4 sine theta. Now you may look at that and go, why in the hell would I replace something nice like x with 4 sine theta, right? I mean, that's going to make it more complicated, perhaps. But this thing was very, very well thought out, all right? Let's take a look at what happens if we do this. Everyone understand the substitution, where it's going to come from? Like how it's dictated, like how you determine what it is? Okay, so erase this. What I'm going to do now is, now that I've determined this is going to be my substitution, right? This is my substitution that I'm going to make. I'm going to write down that substitution just like we did before. And I'm going to differentiate this equation implicitly with respect to theta. Just do the derivative, right? Derivative left side, dx. Derivative right side, 4 cosine theta d theta, right? What I'm doing is I'm gathering information over here. I know I'm going to go over here and I'm going to replace every x I see with this. I know that I'm going to replace dx with that. See, this is not the substitution you're used to where you're trying to look for something in its derivative. No, you're just going to come in and change the problem into something that has trig stuff in it. And somehow it's going to work. All right, the next thing that you should do, and we have never done this before, is take a look at that special expression that made us choose this substitution. Wasn't that the part of this that made us choose this trig substitution? Let's talk about what this is. Now this table doesn't tell you what it is, right? Because I want you to actually know how to get it. Some textbooks, they just tell you what it is, but let's consider this for a second. Isn't this the same as 16 minus, now what's x? What are we saying x is going to be? 4 sine theta. What happens if you square 4 sine theta? What do you get? 16 sine squared theta, right? And what do these both have in common? 16. So you can factor 16 out underneath the root. And what's left when you factor the 16 out? 1 minus sine squared theta. What's 1 minus sine squared theta? Cosine squared theta. And what's the square root of 16 cosine squared theta? 4 cosine theta. Isn't it? And with that, we're ready to go. We're ready to do it. Any questions on where I got that? These are the things you'll do every single time you make a trig substitution. You see which one it is. You'll go off that table and you'll say, okay, I'm going to let x be whatever it tells you you need to be. You'll differentiate it. Then you'll look at that part that has the square root in it and you'll simplify it out, and it should turn out to be something really, really nice. And now we go over here and rewrite the integral. Here we go. I need to call on tables. So back table, Justin, Vanessa, Ruben, Kelly, anyone over there. What's x cubed going to be for me? 4 sine theta cubed. And let's take our time since this is our first one. 4 sine theta, the entire thing cubed, right? That's what x cubed is? All right. You want to keep going? What is square root of 16 minus x squared going to be? 4 cosine theta. Vanessa, you see that? Okay. So that's 4 cosine theta. Ruben, what's dx? That's right, 4 cosine theta d theta. We got it all? See it all? Let's clean this up. We have 4, this 4 is being multiplied times sine, it's being cubed. So doesn't that mean 4 times 4 times 4? Which is 4 times 4 times 4 times 4. Okay, so 64 times 4 times 4. All right, 4 to the 5th power. How about that? You like that? I have 4 to the 5th power, whatever that number is. Integral. So I took this 4, and the 4 cubed, took them all out of the integral. How many sines do I have in here? Just one, right? Sine theta, that's it. How about how many factors of cosine? Oh, wait, sorry, sine cubed. Ooh, bad boy. All right. I forgot the cubed on the sine. How many factors of cosine do we have? 2. Cosine squared theta d theta. And now, guess what? It's a trig integral now. So now you go back to the methods from the previous part of this section. You have sine and cosine mixed together, right? How do you deal with it when you have sine being odd and cosine being even? You're going to pull out a what? 1 factor of sine. I'm going to pull out 1 factor of sine now. You all understand how this works? This is the power of trig substitution, is that when you have an integral that is really nasty, you make this substitution that you think is going to be even worse, and it turns it into something that we can actually handle. Now remember though, our variable here is x, right? What variable are we in now? We're in theta now, so eventually we have to get back to x, don't we? Okay. All right, I need to continue this problem. Anybody figure out what 4 to the 5th is yet, or no? We'll just leave it as 4 to the 5th?
5,024.
Is it 5,024?
1,024.
Oh, 1,024. Integral. All right, you said pull 1 factor of sine out to the back near the d theta. Which means if I do that, what's my u going to be if I do that? U has got to be the cosine now. Oh, shoot. Now I've got u in the problem. So u is cosine theta now. Which means du is what? Negative sine theta d theta. Am I matched up good there? Need to tweak that a little bit? Negative, right? Negative du equals sine theta d theta. So let's see, we're moving up here. Justin, Ernesto, Karen. Can I rewrite this integral completely yet? Well, hold on. We're going around your next table.
Sine squared theta, there's 1 minus cosine.
Yes, that's right. So this part you can handle. This is going to be what, u squared? This right here, sine theta d theta, is negative du. But the sine squared part needs to be converted. We need to switch that to 1 minus cosine squared. All right, so all right. I think at that point we're ready to write it out. All right, so now anything from my happy table here. You ready to rewrite this now? In terms of u, is it ready to go? All right. It will be, I'm waiting, negative 1,024 integral 1 minus u squared u squared du. So 1 minus u squared times u squared, that's du. Actually, that's negative du, which is why the negative came out here. That's a polynomial. What variable are we in now? We're in u now. We got to get back to where? X. But x got converted to theta first, right? So we got to go from u to theta back to x in the end here. Let's see. So this is going to be negative 1024. Oh, I can just go right through this, can't I? All right, so this would have been what? U squared minus u to the fourth? So 1/3 u cubed minus 1/5 u to the fifth plus c. What do you think? We're not done, but what do you think so far? You didn't realize it was going to be this great, huh? Do you remember me having this talk with you about how quickly this subject builds on itself? This is what I mean, okay? So if you can't do trig sub, you can't do, if you can't do trig integrals, you can't do trig sub. It's that simple. All right, so let's go back now. I'm going to leave the negative 1024 out there. This is equal to negative 1024. All right, what was u? Because I forgot. Was it cosine? Okay, so I've got 1/3 cosine theta, but then cubed, and then minus 1/5, and I've got cosine theta to the fifth, and I've got plus a constant. So I'm back to theta. Now I need to go back to x. Do you know what cosine theta is? Do you know what cosine theta is? So go back. What was your original substitution for x? What was it? X was equal to what? 4 cosine theta, wasn't it? Oh, it was 4 sine theta. Oh, shoot. So you mean I don't know what cosine theta is? I know the dx had cosine in it. But hold on. This we know is true, which means this is true. You know where I'm going with this? Reference triangle. Sine of theta is what side over what side? Opposite over hypotenuse. Cosine of theta is what? Adjacent over hypotenuse. Can you get the adjacent? Yes, you can. It's what? Root 16 minus x squared. Now look, we could have cheated. We knew this already. If you look back in, remember when we wrote down those things? I did write at some point, I asked you what this was, didn't I? And we worked it all out, and we did a bunch of stuff, and didn't we get 4 cosine theta? Yes? So we did actually have cosine theta here. We could have just taken the 4 and divided it. And what is cosine theta here according to the triangle? Square root over 4, which is exactly what we got from that. But I'm showing you this because you need to be able to draw a reference triangle, because sometimes what comes out of here will be something like tangent theta. And then you can't go back to this information because it won't contain what you need, and so you have to draw the triangle to get the information you need. So we're there. We made it. We made it to the promised land here. Look, we've got negative 1024. We've got 1/3. Cosine theta is this over 4, right? This over 4. So we have root 16 minus x squared over 4, but then what? Cubed minus 1/5 root 16 minus x squared over 4, but now to the fifth, and then plus c. Of course, that's the antiderivative of x cubed times the square root of 16 minus x squared. Of course. Yeah, I don't know why. I don't know how you got into this class, Alexis. Now that gives you some appreciation of how far we've come, right? I mean, it's a pretty long problem. What do y'all think? Tell me. What are you feeling over there? Yeah. Shall we do another one? Of course we shall. Do you see why I'm not looking forward to trying to do the homework solutions to this section? But this is probably one of the more advanced integration techniques because it does involve so much. There's so much here that can go right and wrong for you. All right, so how about we do A? Let's do A. Integral 1 over x squared square root. Hey, Kiki. Do you remember in that last problem where you were looking and you said we might be able to peel off an x squared, like an x, and do something like that?
And I think that was a bad idea.
Well, no, it's not a bad idea. But from the looks of the answer, I'm not quite sure this is going to work. You know what I'm saying? Like, how am I ever going to get to the answer from here? Maybe it does work, but yeah, I don't know. If you want, Kiki, you can mess around with that. If you get it with that method, let me know. Work it out. I'm not saying it does, but if you want to mess with it, yeah, on your spare time, which I know you have a lot of. All right, what about this one? So we start rolling through the Rolodex of methods, right? Basic substitution, integration by parts. Trig substitution. If I see a square root with something squared and a number, right, then I'm thinking trig sub. So which of the three formats does this look like it falls into? The one that says square root. Oh, it's a squared plus x squared on the paper? Okay. That's the way it is on the paper? But addition doesn't matter, right? This is exactly the same? So that formula can work both ways. The other two can't. Subtractions cannot be flipped inside of a root. You can't pull negatives out of roots, right? Unless you're willing to deal with I. You don't want to mess with I. So that's the same thing. We have that format. For us, it's x squared plus 9, which means x squared plus 3 squared, which means a for us is 3, right? And when you have this form, what does the paper say you should do? What's the substitution I'm going to make? X is a, right? X is going to be a tangent theta, which for us in this problem will be 3 tangent theta, yeah? So we've figured out what form it is, what our A is, what the substitution should be, and exactly what it is for us. What do I do with this now? I'm going to write it down, then I'm going to take its derivative, right? And then I'm going to look at what that square root thing is. May I erase? You don't need that? Okay, so my x is 3 tan theta. Dx is 3 secant squared theta d theta. And then I said you need to look at the square root part that you made the substitution of, that x squared plus 9. All right, who wants that? Zach, how you feeling about that today? It's been a long, you've been doing math all day.
So,
You burned out?
no.
No, you're okay? Okay, so replace x squared with what? 3 tan theta, so it's underneath the root. So what do you get when you square this? So 9, right? 9 tan squared theta. It's what you get when you square x. Then plus what? 9. 9 can come out of both of these. And that leaves me tangent squared theta plus 1. Recognize that. That's secant squared theta. So square root of 9 secant squared theta, which is 3 secant theta. Do you all see that when we do this process, after we figure out what our substitution is, there's basically 1, 2, 3 pieces of information that we need. We need to know what the x is going to be replaced with, what the dx is going to be replaced with, and what the square root junk is going to be replaced with. Once you figure those 3 things out, you rewrite the integral. Got it? Let's see, who have I not called on in a while? I'm going to call on somebody. I don't know why, but on my end, it seems like everyone's talked already today. We'll go around tables again. How about that? So we'll start here. But if you answered me last time, you can't answer this time. Yes, that's what we'll do. So from this table, from this think tank over here, I want you to tell me how to rewrite this integral in terms of theta. So whoever. Go ahead, yo.
You do 1 over,
Will we do a tangent theta, or replace x with the a tangent theta?
Yes. But
Oh,
what is
tangent
that?
Theta, I'm sorry. I was looking at
Yeah,
the far
yeah.
right corner.
We'll get rid of that then. We'll get rid of that.
So we replace that with 3 tangent theta.
Which would
squared.
become, okay, so you want me, I'll just write it as squared. 3 tan, you want to square it now?
Yeah.
Okay.
9 tangent squared theta.
So this x is being replaced with 3 tan theta. It's becoming 9 tangent, you said square theta,
Yes, sir.
times,
The inside, which would be
what does the whole root junk thing turn into?
turned to 3 secant.
3 secant theta. Next table, going back. What's next? You answered last time, didn't you? Sorry.
Replacing the dx.
You got to replace the dx with
3 secant squared.
3 secant squared theta. Matter room. Are we done, Karen? Yes?
No, we can cancel.
Okay, yeah, but I'm saying as far as plugging in, yes, we're done? Okay. All right, so you want to cancel? Tell me what's going to go away here, what we'll be left with here.
Secant theta, no?
Secant, so you're just going to get rid of the squared and that secant, right? Any other cancellation here? These 3's cancel. That's nice. You want to take care of that 9 for me, Karen?
So you can fill it out.
Okay, as
1/9.
1/9. Good. And I'm left with a secant theta on top and a tangent squared theta on the bottom, d theta. Moving on. This one's a little tricky. So I'll open this up to the whole class because this next step's a little tricky.
Are you gonna write it out differently, like 1 over cosine theta times sine square theta over cosine square?
I am going to do that. But why am I not going to do this thing with secants and tangents that we just talked about? I need secant to an even power, which I don't have. Or I need tangent to an odd power, which I don't have, right? That's not going to work. So when you run into a situation like this, where you really can't figure out what's going to happen here, go turn everything in terms of sine and cosine. So usually something's going to work out for you. All right, here we go. So want to turn the secant on top to 1 over cosine theta. Want to turn the tangent squared theta. Tangent is what? Sine over cosine. And squaring them, so sine squared theta over cosine squared theta, then d theta. So I've got a complex fraction. Fraction over a fraction. All right, now we'll move to the next table. We've got Kelly, Vanessa, and Ruben. I knew your names. I was looking this way. I knew all of your names. That's pretty good. I mean, that's a milestone for me. All right.
Multiply the top by the reciprocal of the bottom.
Okay.
Cancel out cosine.
So what would you get? If you do this,
Cosine over cosine theta over sine squared theta.
yes. Everyone agree? Cosine theta over sine squared theta. We'll stay at that table. We're whittling down the members. Vanessa or Kelly, any idea on the technique to get that one? Clear the RAM. Okay, what do you want to use as a basic substitution here? What? Okay, so why sine? Why would we want sine? Derivative's up there, right there, right? Okay. So we're going to do a u is cosine. U is sine theta. I can't talk today. U is sine theta. Du is cosine theta d theta. And so we should be getting 1/9 integral 1 over u squared du, which is the same as u to the negative 2 du. And moving back around. Ethan, Sean, let's see, who's talked over there? Sean, did you answer already? Who answered the last one? Did I skip? I always skip that table. All right, anyone over there? Antiderivative of u to the negative 2. Oh. If the pressure's on, your brain shuts down, right? Just power rule there, right? So add 1 to the exponent. In front of it, 1 over that same number. So negative, you put negative 1 u to the negative 1. Is that fair? Do that. Plus c. And then that's really negative 1 over 9u plus c. That's the same thing. U to the negative 1 is 1 over u. 9's already down there, so I'll just throw them together. I think we're there. But we have to get back in terms of x. Okay, so let's first go to theta, which we already know what u is, right? U is sine theta. So this becomes Ah, man, I should have just left that out there. Negative 1/9 times 1 over sine theta plus c. I peeled it back apart because I realize now I need to substitute back. So I take the negative 1/9 out here. That left me 1 over u. 1 over u, u is sine theta. What is 1 over sine theta? It's cosecant theta, isn't it? Now you could leave it as sine theta down there and then go back to x, but I'm just going to write out what it is. This is negative 1/9 cosecant theta plus c. And now I need to get back to x. So where do I look to get back to x? Where do I look at? My initial substitution, what this technique told me I needed to use. And what was that initial substitution? X was what? 3 tangent theta? X was 3 tangent theta. How am I going to use that? Divide both sides by 3 to create a ratio. And then from that, make a triangle. And label the sides how? Opposite is x, adjacent is 3, and that means the hypotenuse is square root of x squared plus 9. Wasn't that the ugly piece that that's that piece, oh, this piece right here, the square root part of the trig sub that keys you off in the very beginning as to which of the 3 to use? You know what I'm talking about? The square root of the a squared plus x squared, or a squared minus x squared, or x squared minus a squared. That thing will always appear somewhere on your triangle. Always.
Is it always going to end up being?
It won't always end up being part of your answer. But if you draw a triangle, it's going to have to be there. All right, and I wanted cosecant. What is cosecant's the reciprocal of sine? Hypotenuse over opposite. So it's that over this. That's it. So we get negative 1/9 times the square root of x squared plus 9 over x plus c. I don't know about you, but you know, it's good stuff. Now there's one particular type of problem that I want to show you. We've got 20 minutes, so I think I have time for one more. Yes. Come on. This one's not on our sheet there. Okay, I'm doing this one. I'm just going to do this one on my own here. Something's going to happen in here that's going to be kind of nice. I'm doing a different problem, yeah. All right, so you go through and you're like, okay, is this a basic substitution? Do I see something as derivative? No, I don't. Is it integration by parts? No, I don't think so. I don't know, right? You keep on, with time, you start to just get that, I guess. Omit. Cancel. But it has a square root. right? And so which of the formats does this fit into? A squared minus x squared, right? And for us, it's 3 minus x squared, which means that it's the root of 3 squared minus x squared. It just so happens that that's not a perfect square, but that doesn't stop us from being able to use the formula. So for us, a is root 3. What is the substitution that we make in the case that we have this? X is what? What is it? A sine theta? Sure? Hold on, which one are we looking at here? Okay, a sine theta. It's not the last one. It's not x squared minus a squared. I'm not giving you that one right now, okay? The x squared minus a squared, we'll do one of those next class. The reason is because I want you to see this happen, all right? What's about to happen? X is equal to root 3 sine theta. There's what we've got. Okay? So I'm going to go ahead and write this information down. Everything was just to get to that piece right there. Now I'm going to write that down. I'm going to take its derivative, and I'm going to look at that root thing and see what it simplifies to be. How about we take the next 7 minutes to see how far you can get on this? You don't need to turn it in or anything, but let's see how far you can go with this problem in 7 minutes. Let's see, is Joshua here? No? I'm also going to pass around the sign-in sheet. Start here. Make sure that gets around. Just initial next to your name, please.
The only portion of this concept I'm having trouble with is when you investigate that part of it. That's one thing I'm having issues with. like I was having issues with it. I just kind of went along with it
Okay.
beforehand, but if you could like clarify like
Let me see what you did
this
here.
portion here,
So,
then maybe like pull this out, but then where does this squared go? Like I'm not sure.
okay, so let me do it right here. You go square root 3 minus now x squared. So you square this, right? So square that and you get what?
3.
3. Square that. I think you might have missed that. You don't have that written down. You don't have a squared on it.
Yeah.
Okay. Now each of these has a 3.
So that's how you make the square root go?
Well,
Is-
not yet.
is it squared?
Not yet. This right here is root 3, right? I'm sorry, square root 3. Pull the 3 out. That's 1 minus sine squared theta, right? If I pull a 3 out of each of these.
What happened to? I thought this was just originally it was supposed to be root 3, wasn't it?
No, no.
Because you're replacing this with x and you have.
No, no, no.
You get the 3 from this.
This, because this is what in the problem told us to make this substitution, right? To make that substitution, use x equals a sine theta. This is the thing that told us to do that.
So we're manipulating this thing.
Yeah, all we're doing is taking a look at that. We're saying, well, if we're going to make that substitution, then what does that turn into? And that's what we're doing here. We're saying this is going to turn into this because that's what I'm going to turn x into,
Okay.
which turns into this, which turns into 3. This is cosine squared theta. Now, in the previous examples, this was a perfect square. It was 4 or 9 or something. Here it's not, so you can't root 3. But then what's the square root of cosine squared?
Cosine.
Cosine. So that's where the root goes. It goes away because it's multiplication here. It started out as subtraction, now it's multiplication.
Yeah, see, I thought you were trying to manipulate
Nope.
this portion. Right
Nope,
here.
I'm just, it has nothing to do with these. Okay, this is this is our substitution. Here it's derivative, and by the way, the thing we're really looking at here turns into that.
Yeah, because you have to find a, and then x, and then dx, and then the thing.
Yeah.
Okay.
Yeah.
And it looks like that's okay so far. Okay, so now I got perfect. So you're just manipulating the thing that
That's right.
keyed you in on doing this.
Mhm.
Okay, yeah, see, that's where I was confused the previous few
Okay,
problems.
good. As long as that's clear. Are y'all getting anywhere? Does anybody have it down to the trig integral yet? Of what the trig thing, like this with trig stuff in it? Anyone there yet? Yeah? Okay. Just give another minute. Okay, I need enough time to finish this problem out, so let me go ahead and pick up where I had left you. This was going to be our trig substitution, right? We're all okay with that, right? And then take the derivative, so dx, root 3 comes down, derivative of sine of theta is cosine theta d theta. That we always do, right? The next thing you look at that is not connected to this at all, really. I mean, it is, but I'm not like doing the next line or anything like that. I'm just saying, okay, that square root part of the problem that caused you to use this substitution, let's check out what that is. Like, what is this? Because we need to substitute this out. So that's square root of 3 minus x squared. What is x? Root 3 sine theta. So if I take root 3 sine theta and I square it, right? I square the root 3, which gives me 3. I square the sine theta, which gives me sine squared theta. Then from here, they both have a 3. I factor a 3 out. That leaves me 1 minus sine squared theta, which is cosine squared theta. And now I take the root. But I can't take the root of 3 because it's not a perfect square. So I just have to leave it as root of 3. I can take the root of cosine squared theta. That's just going to be cosine theta. So this part right here, this ugly thing, is going to be replaced with root 3 cosine theta. So now I'm going to rewrite the integral. The integral becomes, what is the root 3 minus x squared become? Square root 3 cosine theta. That's it. What's dx going to become? Square root 3 cosine theta d theta. So look, you have got to be extremely careful. You know how these things, dx, d theta, I know on some of your work, you'll forget about the dx and the, you forget these things. Do you see now, if you forget that, you're going to miss an entire piece of the integral? So it's not just something we like to slap on there just to have on there just for fun. It's part of this substitution process. We clear on everything? All right, let's take the root 3 times root 3. Let's take that outside. That's going to be what, 3? And then what do we have inside? Cosine squared theta, which we will use integration by parts. No, that's the one that you had on the test, right? It's the one everyone freaked out about. Not everyone. Some people got it. Right, that's what we have. How do you solve an integral that has cosine squared in it? Use the half angle identity, or what I call the power reducing formula. This is the one where we use, I think the formula, the way I wrote it, was something like this. Remember that formula? No. But instead of x, we're using theta, right? Make sure you keep track of that. You can't mess that up now because, look, we're at theta, we're not at x. So this becomes, let's see, 3 integral 1/2 1 plus cosine 2 theta d theta. Take the 1/2 out. And yeah, we're going to just integrate that. But this is the part of the problem I wanted you to see. Something's about to happen that we haven't had happen, which is interesting. Okay. We can find the antiderivative of each one of these term by term, right? What is the antiderivative of 1? Theta, because our variable is theta, right? Not x. See, again, be careful. So we have 3/2, then theta. What is the antiderivative of cosine 2 theta? 1/2 sine 2 theta, right? Plus c. Hey, we didn't need a u substitution in this one, right? We didn't need a u substitution. We actually just have to go back to x. We're only one variable away. Do you understand? In the past two problems, we were always like 2 variables away. So we just got to go back. But do you see the problem? My answer is in terms of theta, the angle theta, whatever that is, and sine 2 theta. My original problem didn't have 2 theta in it, did it? What is the thing that I told you to go back and look at, though, when you get to this point? Your original substitution, which was x was root 3 sine theta. I said draw a triangle off of this, yes? So x over root 3 equals sine theta. Do y'all see what I'm saying? You don't know what sine theta is. You know what sine theta is. You don't know what sine of 2 theta is. And that's what you need for the answer. Yeah? Also, you don't know exactly what theta is unless you do something over here. But let me draw my triangle. Theta x root 3. Is that right? I'm going to need this side. I may as well get it now. What do you think it's going to be? Square root of 3 minus x squared. Didn't I tell you that that square root thing is going to appear on your triangle? There it is. All right. Let's resolve theta first. How can I get theta? Take this right here. Take arc sine of both sides. Right? Arc sine of both sides. So using this information, I can take the inverse sine on the left and the inverse sine on the right. The inverse sine of theta is going to be theta. As long as theta, we have domain restrictions, but we haven't been messing with those too much anyway. So that's theta, right? And then how are we going to deal with sine 2 theta?
Plug in the two inverse sine.
Oh, you mean multiply this by 2, and then this by 2, and then plug that in? That'd be more work than we have to do. You all remember what this is, right? That's really 2 sine theta cosine theta, isn't it? This is really 2 sine theta cosine theta. Right? This is really 2 sine theta cosine theta. That's what this is. And then the 2 and the half are going to cancel. Do you know what sine theta is? Yes, and you know it off the triangle. Do you know what cosine theta is? This right here. Jason over hypotenuse. So we have everything we need. Here it comes, final answer. The answer is 3 halves, parentheses, theta, which was arc sine of x over root 3 plus the 1/2 and the 2 went away, right? Sine theta, which is x over root 3 times cosine theta, which is root 3 minus x squared over root 3. All of this plus c. We made it. You could put these root 3's together and make that a 3. You could then distribute the 3 halves through, and I think the 3 would cancel. Like this 3 up here would cancel with the 3 down there. We're there. All right, those 2 problems up there, I think I'll have to start maybe next class with those. Here's the homework for this section. Remember that if the integral in the homework has a number up here and a number down here, that you ignore the numbers and just do the problem, but then of course the answers are not correct in the back of the book. They'll have a numerical answer instead of a function, but you can still do it. Yes?
Where's the 2?
Which 2?
Sine theta, cosine theta, right?
The 1/2 in this 2,
Oh.
right? Because this generates a 2 sine theta cosine theta, but there was a 1/2 there. Wasn't there a 1/2 there? Okay. Yeah, because when we did the antiderivative. All right. Well, I would not expect that you could do all of that homework yet, but you should at least get started on that homework. I haven't even started it. The 39 through 61 are problems like this. The first few, they tell you what the substitution should be, like x is 3 sine theta, the first 3 of them, or first few of them. And then from 43 on, they don't tell you what the substitution is. Not that it's super hard to get, but. Have a good day.